Hello, everybody. It's time to go on to a new topic. The topic that we're going to look at now is leading into machine learning and is a topic involving probability. The idea is we want to look at what's called the naive Bayes classifier. It sounds strange, but we'll get there. Thomas Bayes, I got this from Wikipedia. He's in the 1700s, and he basically worked out an example of what became the Bayes theorem. Never published it, but we've given him credit for having the idea. To understand what we're trying to do, here's an example. We have a piece of email which has the word $1 million in it. Now, do we think that is spam? What is the probability that this email is spam? Well, what do we know that we might be able to rely on? Let's see. We can estimate based on our experience or surveys of the probability that a given email X is spam. We know that. We can guess that. We can do it by just looking at a sample. And we can estimate the same way what the percentage, what's the likelihood that the word $1 million is in the email if we know that the email is spam. Maybe $1 million is too low these days. Maybe we put it in $10 million, but whatever. Now, I want to make sure we understand all these terms, but I'm trying to start out with some idea of why we would want to do this. If we could do this, we could set up some form of spam detector and pass the information in and determine, well, we've seen the word 1 million. The probability is X. If that's too high for us, we're going to quarantine that. So that's one way of doing this. Now, there are other examples involving medicine that we're going to look at too. Before we do that, I want to refresh your memory about some probability. So let's talk a little about probability. So just this will be our topic here. And we'll see what we have. Many of you have probably taken a probability class. And if you've taken the lower level one, you're probably closer to what I'm going to be doing right now. If you've taken the upper level one, you probably use calculus in what you were doing. We're not going to do that. We're using a rather naive type of probability here. The first thing to realize is that we have a universe, just a fancy name, of possible events. For example, I roll a die, six-sided die. I have 6 possibilities for what number is going to come up on top. So those are the 6 events that could occur. So I'll put that in here. Example, if we roll one die, one 6-sided die, then we have 6 events. Row is 1, row is 2, and so on. And I'm not going to keep going. I think you get the hint. You've probably seen it enough times, etc. So each of these events can happen. The probability function is a function which has values between 0 and 1 inclusive. It can never be greater than 1, and it can never be less than 0. So we're going to say, for example, the possibility that it will rain tomorrow is 0.6. We don't say 60%, although loosely we fall into that. But these are fractions, decimal numbers. Decimal numbers say between 0 and 1. The probability the probability of x1 plus the probability of x2 plus the probability of x3 plus the probability of xn, where we have n possible events, is 1. The possibility that one of the events will occur, some one of them, is 1. Now that helps us very much because it means that we can say, if we have the probability that x is the outcome, then the probability that x is not the outcome, well, those are the only 2 possibilities. X is or X isn't. So it's got to be 1, which is the total possibility, minus the probability that X is the outcome. That can be used sometimes when we want to calculate some things. We have one of the probabilities, we can get the other one easily. So these are numbers. And how do we get them? Well, we can estimate them. These numbers by taking samples. Or maybe we can work it out mathematically. And in the real sense, that would be the better way. But I'm just going to take some samples here. So example, suppose we roll one die. And unless you're walking around with a loaded die in your pocket, we think that each of the sides is equally likely. So the probability that a roll is 1 equals 1/6, which is, I think, 0.16 something, 96, 2/3, something along that line. Now, the way I got that is I know there are 6 possibilities, 6 possible outcomes, and only one of them is 1. 6 possible rolls, let's say. So that wasn't too hard. We use that all the time. Second example, suppose we roll 2 die, or 2 dice, I should say. Again, 6-sided. What is the probability that we roll a 7? Well, let's look. We could roll 1, 1. That's one possibility. We could roll 1 and a 2. We could roll 2 and a 1. Not the same, because there are 2 possible ways we could get the 3. We could roll 1 on one die and 2 on the other, or vice versa. Then we could also roll 1, 3, and 3, 1, etc., and etc., and etc. What that really means is we have 6 possible values of the first die and 6 of the second die. So we have 6 times 6 possible rolls. Those are the things that can happen. So now we can decide how we're going to figure out if we roll a 7. Well, how can we roll a 7? We can have a few different ways. Let's see. To roll a 7, we could roll a 1 and 6, or, pardon me, or a 6 and 1, or a 5 and 2, or 2 and 5, or 4 and 3, or 3 and 4. Now, I think I've done all the possibilities. If I went down to 2, I'd just be repeating the ones I already had up there. Because remember, I had a 2 and a 5, or a 5 and a 2. So how many did I get? 1, 2, 3, 4, 5, 6. We have 6 rows that give a 7, and 36 rows total. So probability of a 7 equals 1/6 again. Yes. But the probability of, say, we roll a 2 would be much different. There's only one way in row of 2, that would be 1, 1, so it'd be 1/36. So this is the way we take care of this. Now that's elementary, I hope. I hope that doesn't get too far past your reasonable understanding of probability. We're not involved, we need the probabilities, but we're going to be defining something different than that. What we're going to be defining is what is called conditional probability. What this says is, what's the possibility that something will happen if I know that something else has happened? So the probability that X will happen given that Y has happened, that Y is happening. That's what we mean. That's a conditional. It's the conditional probability of X given Y. Now there's some reasonable examples of this. What is the probability that a patient is coughing given that the patient has a cold? That's a reasonable thing, and we could easily estimate that. We take all the patients that come in who have a cold, and we see which ones of them are coughing and which ones aren't, and we divide the number that are coughing by the number of patients. So that seems reasonable to define. Now, the interesting thing about Bayes is, if we know that, and the probability that people have a cold, and the probability that people are coughing, we can go backwards. And we can say, what is the probability that you have a cold if you're coughing? This is what the doctors would want to do. You come in with a set of symptoms, and we want to know what is the chance that you have a particular disease based on those symptoms. That's where Bayes comes in. It works in that particular setup. So let's see what we can do. I'm going to define something here. P of X given Y. Now think about this. How could we do this? Well, we could take all the probability that Y happens. How many times does Y happen? And then we could find out what number of them also have X. So we took the probability of X 2, 2, 8, no, wrong one, 2, 2, 7, and Y, divided it by the probability of Y. It seems like we would get the probability of X given Y. Think of it this way. You're separating out all the chances that there's a Y. So let's say that there's a 0.3 chance that someone has a cold. Now, of those 0.3 people, 0.7 of them pardon me, 0.1 of them, 1/10, have a cold. So it'd be 1/10 over 3/10, or 1/3, which seems to make sense. We're saying that we don't expect to have that many coughing, because only 1 out of 3 people that come to us are coughing. Now that is perfectly mathematically correct. Here is the little quirk or trick. Let's take the probability that y given x. Well, by the same reasoning I had up above, this is the p of the probability of x and y divided by the probability of x. And there's a same thing in both of them. The p, x, and y. So now we can say, well, let's see. I would like to know the probability of x given y, but I already know the probability of y given x. So why don't I do it this way? I'm going to take this here, and I'm going to rewrite it this way. I'm going to take the p of y and put it times both sides. And this requires, of course, that the p of y is not 0. So I'm going to get that. And by the same token, I can use the other formula to say that that is the p of y given x times p of x. What I've done is solve both equations for p of x and y and made the two solutions equal, which of course just simply means that we take this and rearrange it once more. We get rid of this middle part because you don't need it anymore. And we put this in parentheses and divide by p of y. This is mathematically correct. However, there are people who just don't like it. And your next writing assignment is going to be to look up some of that information on the web. The reason they don't like it is that they think this is backward reasoning. What this basically says is the following. Let me get this up here. This says, if we know probability of x and the probability of y and the probability of y given x, we can compute the probability of x given y. And I guess the best example would be we know the probability of someone has a cold. We know the probability that someone is coughing. Pardon me, I'm not getting that spelled right. And we know the probability that someone is coughing given that they have a cold. So now, if a patient walks in with a cold, with a cough, we can compute the probability that they have a cold, given that we know they're coughing. It seems backward to some people. It seems like we're reasoning backwards. And yet it's perfectly okay, and it's been used continually. In fact, the funniest thing is we make an assumption later when we do the more advanced part of this that basically says this assumption is wrong, but it works. And we're going to do it anyway. It works most of the time. This item right here, this is the Bayes theorem. It's the simple Bayes theorem. There'll be a generalized Bayes theorem that will put a little more in it. That's really all it is. That's all we're talking about. It's not hard. It doesn't really give us much trouble. I think I have an example in another sheet over here, which I'll bring up and see if I can copy over. I don't want to do the generalized yet. This is an example using cancer. The spam example I gave before is a possible example. So I want this one. I think I have an actual worked out one. That's coming later, so don't worry about it. There's a possibility. The example with if we know these items. Let me go a little better. Just get this part. And I'll bring that over to what we were doing. So this is the example. And it simply says, compute the probability that the patient has a cold if the patient has a fever. That's what we want. And I made up some figures here. I guess I left them on the other sheet, so I better go and get them. Yeah. These are the things I was supposed to take with me, but I didn't. Sorry about that. And then I'll go over here and put this here. Actually, I'll put it here. And those are the things we know. And now there's the computation. So the first thing we're going to do is have you, I'll probably give you I hope a simple homework just involving that. Then the next video we'll talk about the generalization of it, which will take us to the naive Bayes classifier. But let's just do this one right now and then go to that one probably tomorrow or the day after. So long now. See you later. Don't forget you have no, I guess you don't.